Okay, so in this video, I'm going through the study guide questions about structures and IMFs. So first question, how can we identify structures by looking at the formula we're given? So I guess we'll talk about each structure and how you know. So the first structure, well, not the first, but one of them is ionic. And you know it's ionic when you have ions that make it up, obviously. So what do you look for? Well, you look for metal plus non-metal, or any polyatomic ion. So if I see something like magnesium fluoride, metal, non-metal, ionic. Or if I see something like ammonium sulfide, polyatomic plus an ion, that's going to be ionic. So these are both going to be ionic structures because we have ions. And again, you look for metal plus non-metal, or you look for any polyatomic ion. Another one would be metallic. And this one is very obvious. You're just looking for metals, like just one metal. So a metal. So, you know, something like Fe or Ti or Cr, you know, there's like 100 metals out there. Another one would be molecular. Molecular are molecules which are bonded covalently, and you're looking for non-metal plus non-metal. Or you're looking for metalloid plus non-metal. There are exceptions to a lot of these. You'll learn about some when we talk about network covalent, but in general, non-metal plus non-metal or metalloid plus non-metal is going to be molecular, such as CO2 or H2O or PCl3 or GeH4. These are all going to be examples of molecular compounds. And the fourth type of structure we talked about was network covalent. Network covalent, you're looking for specific examples that we've talked about. Two of them were this, C, carbon, which can take the form of diamond or graphite. Diamond or graphite. Another example was SiO2, silicon dioxide, sometimes called silica. That's like what makes up sand and glass. And another example would be Si, which is just silicon. So these four really are going to be examples of network covalence. So you just want to look for those specific examples. Sketch an example of each type of structure and state what forces hold it together. So let's start with ionic. Ionic, you're looking at ions that are held together closely and in a nice orderly fashion in all three dimensions. So it's going to look something like this. Yeah, I could just keep sketching this forever. But they're basically all held together in three dimensions. You're not going to really only draw this two-dimensionally, but these are going to be held together in a three-dimensional shape. And in between all of these, we have these bonds here. And what are these bonds? These are ionic bonds. And of course, this is like, you know, three-dimensional shape. I'll just do one more layer. So like that's bonded to that, bonded to that, that, and so on. And of course, these are bonded, these are bonded, these are bonded. You get the idea. So we're looking at a network of ionic bonds that hold the ions together in an ionic structure. Let's do molecular. So in molecular, you're going to have, you know, an atom here and maybe another atom there. And these are going to be covalently bonded together. But importantly, the structure is going to be only held together by IMFs, intermolecular forces. So if that's what the individual molecules look like, these are only going to be linked with IMFs. IMFs. Okay, which is going to give them weakness. It's going to make them not quite as strong, not quite as high melting points, things like that. Let's look at metals. So metallic structures. Well, here we're going to have atoms of the metal are all held together closely, and the electrons can become delocalized, meaning they can leave their parent atom and go flow freely. So really, these are no longer atoms, they're now ions. So this might be, I don't know, name a metal, vanadium. So that might be like a V plus, V plus, V plus. And we have all these electrons that can freely flow in and around and throughout. And we refer to this as the sea of electrons. So what holds this structure together? You would call it the sea of electrons, which is sometimes called metallic bonding or metallic bonds. And lastly, network covalent. In a network covalent structure, we're talking about covalent bonds that hold it together, like we see within molecular, but the difference is the entire thing is completely covalently bonded together. It's a constant pattern of interlocking covalent bonds, and that gives it incredible strength. So we might have, let's say, a bunch of carbon atoms like this, and these are going to be completely interbonded with covalent bonds throughout. You know, you get the idea there, completely bonded throughout with covalent bonds. And this would be something like diamond, if it's completely bonded. If it's bonded in flat layers like that, you know, like something like, I'll try my best to draw it three-dimensionally, where we have ionic bonds that hold like these together in a sheet and these together in a sheet, but then this would now be like graphite, where we only have IMFs that hold the sheets together. So it's very strong one way, but not the other way. So these are the structures. Once again, ionic compounds are held together by ionic bonds. Molecular compounds are held together by IMFs. But please note that the molecules themselves are held by covalent bonds. Those are the intramolecular forces, but the intermolecular forces between molecules are IMFs, intermolecular forces. Metallic bonds, you have the metal ions held together by the sea of electrons or metallic bonds. And network covalent, you have all of the atoms or molecules completely interlinked with covalent bonds. Okay, let's see whether these are going to be soluble in water. So the idea behind solubility in water is like dissolves like. So a polar molecule like water can dissolve polar solutes, water is the solvent, or charged ions. Basically, water has a positive end and a negative end. That allows it to grab onto charged molecules or polar molecules and pull them out of solution or out of the structure into solution. If something is unable to, if there's nothing for the water to grab onto, then it can't really pull it apart. Okay, solid potassium chloride, KCl. Well, this is ionic. So this is going to be, I'm just going to check yes for soluble and X for insoluble. Yes, that's going to be soluble. Why? Because ionic compounds have ions, charged ions that the water can grab onto and pull apart. Solid silicon dioxide, no. That's held together by very strong covalent bonds in a network covalent structure. You should just remember SiO2 is one of our examples. And there's nothing really for the water to grab onto there. Solid titanium, no. And we know that. We know metals aren't soluble in water. And that's because the sea of electrons kind of protects all of those. There's nothing for the water to grab onto and pull away. You know, it can try to do so, but the electrons are going to hold it in place. Solid phosphorus trichloride, a polar molecule. Yes, that is soluble because like dissolves like. So polar water can dissolve polar solids like phosphorus trichloride. Tricarbon octahydride, that's nonpolar, so no. Like dissolves like, so a non-polar molecule will not dissolve in a polar solvent like water. Interestingly, that would dissolve in a non-polar solvent like a type of oil. Next question, state whether these would have relatively low or high melting points and why. So when it comes to melting points, we want to think about the strength of the connections between the particles. And we can look back at the pictures we drew. Which ones of these yell strength? I would say ionic, definitely. A strong network of interconnected ionic bonds. I would say metallic, definitely. A strong network of metallic bonds, sea of electrons. I would definitely say network covalent as well. A strong network of covalent bonds holds those together. So really the only one that shows weakness to me is molecular, because while the molecule itself is held by covalent bonds, intramolecular, the separate molecules, neighboring molecules, are only held together by IMFs, which is not a bond, but just an attractive force. So that's why molecular is going to have the low boiling point, low melting point, and the other three are going to have high. Now, we tend to not rank ionic versus metallic versus network covalent. For now, we'll just say those are high, molecular is low. So going back to the list, chromium is a metal, so we can say high. Ammonium phosphide is ionic, so we can say high. How do I know that's ionic? Because I see a polyatomic ion in there. Sulfur trioxide, low, because that's covalent or molecular. It's held by covalent bonds. How do I know that's molecular? Sulfur is a nonmetal, oxygen is a nonmetal. Nonmetal, molecular. Graphite, I recognize that as one of my network covalents, so that's going to be very high. Next question, electrical conductivity. Now, when it comes to electrical conductivity, in order for something to be a conductor, you need charged particles to be able to move in the same direction. Solid cobalt, that's a metal. Yes, that's going to have great electrical conductivity. What's the charged particle that's able to move in the same direction? Electrons. Now, normally when we look at electrons, it's random movement. But if you introduce a voltage, which is a positive force on one side and a negative force on the other, that will direct all the electrons to flow in one direction. That's your electricity. Solid titanium 3-chloride. That is not going to conduct electricity. We have charged particles, right? We have ions, positive and negative. But the problem is they're not able to move around when they're solid because they're locked in that ionic prison. The ionic bonds hold them in place so they can't move. Aqueous titanium 3-chloride. Yes, that is going to be a conductor because you have charged particles that are now able to move around. Because they're dissolved in water, they're able to move around and conduct electricity. Aqueous C12H22O11. So I recognize this as molecular. In fact, I recognize that as sucrose, table sugar. This is not going to conduct electricity because while we have particles that are able to move around, none of them are charged. We have sugar molecules. There are no charges there, so there's nothing to conduct. And I guess I forgot to do an example of a network covalent, but those are not going to conduct either because there's nothing solid. There's nothing charged that's able to move around. Okay, on to IMFs. So when it comes to IMFs, basically, all molecules have London dispersion forces. It's what I call the participation trophy of the IMFs. If you exist as a molecule, congrats, you have London dispersion forces. And what are those? Well, it's the temporary polarity caused when the electrons of one shift a little bit to one side, the protons shift a little bit to the other side, and just for a split second, you have a teeny bit of positive and negative, and that allows a little bit of attraction between molecules. It only lasts for a split second, it's temporary, which means it's very weak. If you're a permanently polar molecule, which we will tell you whether it is or not, you can see right there, then you not only have London dispersion, but you also have the next level up, which is dipole-dipole forces. That means that you're always positive on one side and negative on the other. That creates a stronger intermolecular force. Well, the third one is hydrogen bonds. How do you have hydrogen bonds? Well, not only are you polar, but you actually have the weakest nonmetal bonded to the strongest nonmetal, meaning hydrogen, the weakest, is bonded to one of the three strongest, N, O, or F. So if you have H bonded to N, O, or F, it creates a very large difference in charge from one side to the other. And that creates very high polarity, which is a very strong intermolecular force. So hydrogen bonds exist when a molecule has H bonded to N, O, or F. Please note, if you have H bonded to any other element, it doesn't count as a hydrogen bond. Okay. SO2 is polar, which means we have LDFs, because all molecules do, and we have dipole-dipole. Do we have hydrogen bonds? No, because there's no hydrogen. CH4 is nonpolar. We have LDFs because everything does. In fact, let's just go ahead and write this down. LDFs, LDFs, and again, that's London dispersion forces. CH4 is nonpolar, meaning that's it, no more. Now, hold on a sec, doesn't that have hydrogen bonds? No, because the hydrogen is bonded to carbon. It's not bonded to one of the big three, N, O, or F. NH3, we say that's polar, which means you also have dipole-dipole. Let's see if this also has hydrogen bonds. Yes, it does, because we have NH3, meaning no matter how it's configured, you will have N bonded to H at some point. So this will have H bonds. And finally, F2, nonpolar, LDFs only. Next question. This relates to boiling point. Why do polar molecules tend to have higher boiling points than similar sized nonpolar molecules? Well, it comes down to IMFs. The stronger a molecule's IMFs, the closer its neighboring molecules are held together. In other words, the harder it is for them to be pulled apart or moved apart due to heat. So the stronger the IMFs, the higher the boiling point. You have to work harder and put in more energy and heat to separate them when they have stronger IMFs. So the weakest IMFs are London dispersion forces. And if you only have that, you're going to have a low boiling point. The next level up is dipole-dipole. If you have dipole-dipole, you will have a higher boiling point than if you just have London dispersion. And of course, the greatest IMF of all is hydrogen bonds. If you have that, you actually have all three, and you're going to have a much higher boiling point than a similar sized molecule without it. So why do polar molecules tend to have higher boiling points than nonpolar? Because polar molecules have dipole-dipole forces in addition to London dispersion, and nonpolar molecules only have London dispersion. Next question there. Why do larger molecules tend to have higher boiling points than smaller molecules? Well, that's because the larger the molecule, the more protons and electrons there are to create that temporary dipole force of London dispersion. A small molecule or a small atom is going to have a small shift in its protons and electrons compared to a larger atom or larger molecule is going to have a larger shift, which creates a more effective London dispersion force the larger it is. So that's why larger molecules are going to have higher boiling points, because they have stronger London dispersion forces. Finally, a real-life example. Water and methane, CH4, are similar sized molecules. You can see the molar masses. Yet water boils at 100 degrees Celsius, while methane boils at -162. What accounts for this difference? It all comes down to IMFs. Methane, I guess I should have told you, I think I said it a couple slides ago, methane is nonpolar, meaning it only has London dispersion forces. That's why it has such a low boiling point, because it's only held together by the weakest of the weak. Whereas water is polar, so it has dipole-dipole, and it has hydrogen bonds. So water has all three types of IMFs, which give it an incredibly strong, incredibly high boiling point, impressively high boiling point for its size. Okay, hope that helped. Good luck studying for this and the rest of the quarter 3 test.